All right, let's go ahead and get started for today. Before we begin, are there any questions anybody has concerning the lab or anything else? I want to point something out. A student brought this to my attention, and it's worth explaining to the entire class. In the pre-lab, the student was concerned because the relationship between voltage and current in the diode in the simulation did not match the equation that we've already been using, where ID is equal to IS e to the VD over N VT. And they were concerned that there was something wrong. Actually, no, there's nothing wrong. This equation, the ideal diode equation, or I should say the p-n diode equation, I should say. The p-n diode equation is a first-order theoretical equation. What you're going to find is when you simulate a diode in LTspice, unless you use the basic diode model. So for example, you've got a 1N4148 diode, an actual silicon diode. The model they use is much more complex than just what that simple little equation does. They factor in all the non-idealities, including the fact that there's contact and material resistance in the materials used to make up the diode. So what you're going to find is, when you do simulations, they're not going to perfectly match what you're going to see here. Now, obviously, if they're 100 times off, then there's something wrong. But if they're 50% off or something like that, in general, there may be nothing at all wrong, simply beyond the fact that you're looking at a non-ideal model versus this equation we're using in class. So these types of simple equations, as I said before, do not account for things, for example, like reverse current and other non-idealities. There are second and third order issues, third order terms that are involved in these. So don't be worried about the fact that you don't exactly match, but you do want to look at this and make some reasonable comments in terms of what you're seeing. Now, also, I should point out that these equations and the simulations are not going to match, and what you measure in the lab is not going to match either, because all components have tolerances. So the LTspice model is basically an average or a mean of all of the different all the different characteristics of those diodes. But in this case, your particular diode may have something, a different tolerance, and may have a particular value that is quite a bit off from what the simulation would tell you. So again, don't be surprised by that. Don't be shocked. What you're learning here in this class is there is a difference between hand calculations versus simulation versus measurements. And you're going to see this as you go through the semester. This should not be a surprise to you. Now, as I said, obviously, if they're huge, if they're orders of magnitude different, there could very well be something wrong. There probably is something wrong. But if you're seeing tolerances 20%, 50%, something like that, doesn't necessarily mean there's anything wrong. It simply may be that for the particular circuit you have built or that you've constructed and measured, that you are seeing variances from the simulation model and from the ideal calculations. So I always want to bring this up. This is your first experience with electronics from seeing that the real world doesn't match what the data sheet says, nor does it match what the equations in the book say. You're always going to have some tolerance, some variance from those values. So just wanted to bring this up just in case people were kind of concerned about what they were seeing. I would be very shocked if your hand calculations exactly matched what the simulation said. You're always going to see some difference between them. So just worth bringing up to everybody. All right. Any other questions? Any comments? Okay. Let us return to our topic last time. We were looking at small signal analysis, and as I talked to you last time when I drew this little diagram, you're going to be doing this pretty much for the rest of the semester. What you're going to be doing is you're going to have a large signal model, which is typically, not always, but typically is going to be a nonlinear model. You'll be given the equations, and you'll have to calculate the DC bias point of the circuit from that large signal model. Then given that Q point or bias point, given those DC voltages and currents, you're going to see you'll need to plug those into the small signal model because the DC bias point affects the values in the small signal model. And then you can put in your AC inputs and get AC outputs. And this is a linear analysis problem. So in this regime over here, it's circuits 1, stuff you guys have already seen. And as long as you remember your circuits 1 and you can do nodal analysis, everything's going to be set there in front of you. You're going to be given the diagrams. You're going to be given the equations. All you have to do is apply them properly. So let us look at how we can derive a small signal model for a PN diode. And not only for the PN diode, but also for all of the other components that are in the circuit. Because if we're going to do a calculation in the AC domain, we have to have equivalent models for every component in the circuit. So just remember phasors when you guys did it in circuits 1. We had to look to see how to create a circuit where every element was in the frequency domain. We'll have to do the same thing here. So in this case, oh, actually, first, before I begin, I want to first clarify something. As we now move into the discussion of small signal models, we want to get our terminology straight. And I'm going to be sticking with this terminology from now on. When you're talking about DC voltages and currents, for example, when you're calculating bias, those are always going to be uppercase variables and uppercase subscripts. AC voltages and currents are all going to be lowercase. So in this case, both the variables and the subscripts will be lowercase. Sometimes we'll have a voltage or a current that is a combination and has both a DC and an AC component. In which case, we'll have a lowercase variable but an uppercase subscript. So up to this point, I haven't always been strict on this. I've just been kind of doing it willy-nilly whenever I went through and defined my variables. But in this case, from now on, we're going to follow this convention. So all uppercase, DC. All lowercase, AC. Uppercase subscripts with lowercase variables. Then you've got an AC and a DC component of that voltage and current. So we'll use this, and the book uses this convention as well. So just wanted to get these terminologies correct. Now let's talk about our small signal model for the diode. Okay, now, first of all, the small signal model is only going to matter to us when the diode is on. So we're going to look at the small signal model assuming forward bias. Now keep in mind, small signal analysis assumes a linear circuit. So what we want is there's going to be something in this box. It's going to be 2 terminals. And we want it to have a linear relationship between VD and ID. So let's think for a moment. Let us cast our minds back to that time long, long ago when we were in Circuits 1. Actually, let me take this off here because I realize I don't need it right now. Let's go through, and in this case, we need a linear element with voltage versus current. It's 2 terminals. What did we learn about in Circuits 1 that was an element that had those properties? What element had those properties? I'm sorry? Resistor did, yeah. A resistor, right? Doesn't a resistor have a linear relationship between voltage and current? Yeah, sure, absolutely. Ohm's law, remember that. So it would seem that a good small signal model for a diode is going to be a resistor. And in fact, let's go through and let's figure out what kind of resistor model we can use to represent that diode. And what we're looking for is, if we shift the AC and the DC currents, the AC voltage and DC current of the diode by a small amount, we want to represent that with some resistance R sub D. So V is equal to I times R, or delta V is equal to delta I times R. So that's the kind of equation we want. Or we want to see how this resistance behaves as we vary the voltage and current around a particular Q point. So we want to evaluate those at a Q point. Now, we make those deltas smaller and smaller and smaller. And what do we turn this into? Derivative, yes, exactly. So we're going to take those derivatives, and once again, we're going to evaluate the result of that derivative at some Q point, at some particular DC bias value. So let's go ahead and let's do that. We know that VD is equal to N times VT times the natural log of ID over IS. So that's the diode equation for the DC voltage and the DC current. Let's plug this into this derivative. And so this will be equal to the derivative of N times VT times the natural log of ID over IS with respect to ID. Again, evaluated at whatever Q point we're going to do. And if I do this derivative, and what we're going to have to do is split it up into 2 logs and then take the derivatives of the 2 logs. But if we do that, I'm going to skip the math, we'll get the following. We'll get it's equal to this. That derivative evaluates to this. N times VT divided by ID at a particular Q point. Well, in other words, it's equal to this. It's equal to N times VT divided by IDQ. In other words, the quiescent DC current or the DC bias current. So there we have it. In this case, we're going to replace our diode in the AC domain with a resistor with that value, N times VT divided by IDQ. So we have a diode that's operating at a particular bias point, a quiescent current and a quiescent voltage, IDQ, VDQ. In the small signal domain, we replace that diode with a resistor with a value of N times VT, the thermal voltage, divided by IDQ. Let me draw that a little bit nicer here. I didn't write that very well. And there's our small signal model. Now the nice thing about this is this model works for every diode. As long as it follows that P-N diode equation and it's forward biased, all we have to do is plug in the value of N, the slope factor, the thermal voltage, and also whatever quiescent DC current that diode is biased at. And there's our small signal model. Now, this is our small signal resistance. You'll also see this called sometimes the dynamic resistance. Or sometimes it'll just be called the AC resistance. So you can see any one of those terms applied to this, but the book will sometimes say dynamic resistance as well as small signal. Question? Yes,
So originally the idea is that it's AC, but then we turned it into DC. But then at the bottom, when you showed the diagrams, it looks like, oh, it's a diode with DC, and then we turn it into a resistor with AC.
That's correct. That's correct. So in other words, this is the representation of this equation. So this diode is biased at this region of operation, a DC current and a DC voltage across it. And in the AC domain, it will be represented by a linear resistor with a value of NVT over IDQ. Okay? All right. Questions about this? Yeah?
So we are basically assuming that after we transform it to a resistor, then the AC current and the AC voltage, like the small AC current, small AC voltage, is not impacted.
Well, the AC voltage and the AC current are going to be the result of an AC source that we apply to the diode, which we haven't shown yet. Okay? So once I go through and work the rest of the problem, this will become clear to you. So yeah, for now, these small signal AC voltages and currents are not the result of the bias. They are a result of AC sources being applied to the model. Yeah?
Does this assume small amplitude AC source?
Yes, we are. As always, we are assuming the small signal assumption that the AC sources are small compared to the DC bias values. So in terms of their magnitudes. Now, as we said before, sometimes in some circuits that's not necessarily true. Sometimes we can have large AC amplitudes, which means the small signal model is not as accurate, but it's still useful, so we still use it. But yes, it becomes most accurate when the magnitude of AC is very, very small compared to the magnitude of the DC. All right? Any other questions? All right, now if we're going to use this resistor, this dynamic resistance for calculations, it's not enough just to transform the diode. I have to transform the other elements in the circuit as well, just as we did with phasors in circuits 1. Every element in the circuit has to be transitioned over to the correct domain. So let's consider how we would transform other elements. Yes?
When you say transform other elements, do you mean things like the voltage itself and then?
Well, yeah, in other words, we're talking about the other elements in the circuit. So yeah, I'll show you in just a moment here. In other words, we need an AC or a small signal equivalent of every other element in the circuit if we're going to do analysis for that circuit in the AC domain. So let us consider large signal versus small signal. we have to transform all of our circuits into the small signal domain, or all of our elements. So what kind of things do we expect to see in the circuit? Well, we may see a DC voltage source. Now let's consider what the AC resistance of a DC voltage source would look like. Where that resistance is the derivative of the voltage with respect to the current, just as we did with the diode a minute ago. What is the derivative of the voltage with respect to the current? 0, yeah. In other words, the voltage never changes. A voltage source doesn't care what current flows through it. It's always going to be the same voltage. So dVdi is just equal to 0. And therefore, in the small signal domain, a DC source just becomes a wire or a short circuit. And this should look familiar to you from circuits 1. You saw this kind of thing before, right? Let's consider a DC current source. And in this case, I'm going to flip it around. I'm going to look at the conductance. And in this case, I'm going to ask, what is the change in the current with respect to a change in the voltage across a current source? 0, right? If the conductance is 0, therefore the resistance is infinity. And therefore, a current source becomes an open circuit. Then we're going to have resistors. And let's consider just a standard resistor. What is the value of dVdi? What is the AC value of a resistor? R, it's still R, exactly. It's just equal to R. And so therefore, in the AC domain, in the small signal domain, resistors do not change. Like I said, this should look familiar to you. This is very similar to what we saw when we did phasor analysis in circuits 1. You saw the similar types of transformations. All right? Okay. So now we've got other elements we need in order to make this work. Now we're also going to be adding in, for example, AC voltages and currents whenever we go over to the small signal domain. But when we're in the DC domain, this is a transformation we have to do to get over to the small signal circuit. All right, let's go through and let's work an example. All right, here is a circuit that has both a DC source applied to it and an AC source. So the DC source is 5 volts. The AC source is a 10 millivolt peak-to-peak AC source. And what I want to do is, given the quiescent voltage and current of that diode, I want to calculate and find out what will be the AC value of the voltage across that diode. All right? So we're going to find V out. we are going to assume that N is equal to 1. So unless I tell you otherwise, we're typically going to say N is equal to 1 and the thermal voltage is equal to 25 millivolts, as you've already seen. Okay. Oops. All right, the first step in our analysis is we want to calculate the Q point, the DC bias point. So to do this, I am going to zero out the AC sources. I'm going to use superposition. So as you're going to see, we're going to use superposition a lot, where we're going to zero out AC or sometimes DC sources and just ignore them while we're doing the calculations for the other domain. So we do that first. Then we calculate our voltages and currents, and I'm going to apply the constant voltage drop model for that diode. I'm going to assume that VDQ is 0.7 volts. Constant voltage drop makes things easy. And therefore, IDQ will be equal to 5 minus 0.7 divided by 10K will be equal to 430 microamps. So there's my quiescent voltage and quiescent current for that diode. Now, I could have iterated this and spent time getting the exact value, but as we've already seen, if you use the constant voltage drop model, you're generally going to get within a few percent of the correct answer right off the bat. It's a quick, simple approximation. All right, second, let us replace all of the elements with their small signal equivalents. So I'm going to take the AC source before that I zeroed out. I'm going to restore that. And then every other element, I'm simply going to transform. So in this case, my 10 millivolt peak-to-peak source is back. My DC voltage source becomes a wire. My 10 kilo ohm resistor does not change. And I replace the diode with its small signal equivalent resistance, which in this case, RD, is going to be equal to that'll be equal to 58.1 ohms. So I've got a 58.1 ohm resistor here. Now, how do I calculate V out? I could do nodal analysis, I could do voltage division. There are 1,000 ways to do it. At this point, this is nothing but linear circuit analysis. So in this case, I'll just say that V out is equal to 10 millivolts times 58.1 divided by 10,000 plus 58.1. I'm just using the voltage divider equation. And this will be equal to 57.8 microvolts peak to peak. And there we go. So like I said, this is kind of similar to some of the stuff you've already seen in circuits 1. Not quite, but similar to it. Take everything, transform it over, and here it's, once again, just the stuff you already know how to do. Yes?
So even though it says that we can treat it as a DC source when we're doing the...
Well, you treat this as you have the DC source in the circuit whenever you are calculating the bias point. So I calculated the bias point with this circuit. So if I want to calculate the DC voltage and the DC current, the only thing that matters is the DC source. I zeroed out the AC source, not in the circuit for the DC calculations. Then once I completed that calculation, then I transformed and went over to the small signal domain. In that place, the DC source goes to a wire.
I was saying like for on your last original there, we can just treat the AC source as just one side.
Yeah, in other words, I'm treating it as a 10 millivolt peak-to-peak signal, so I know my answer, my output's also going to be a peak-to-peak answer. So this is actually going to be some type of perhaps sinusoid. It could be, however, it could be some other type of, periodic AC waveform. I'm assuming it's sinusoid, but whatever it is, I'm saying it's 10 millivolts peak-to-peak. It could be voice. It could be a voice signal with a peak-to-peak value of 10 millivolts, right? It could be anything. I'm just saying it is an AC signal which is very small compared to the DC values. All right? Now, questions about this? Yeah?
So is this 10 millivolts like going about the Q plane?
No. Well, yeah, probably yes. What we're saying is the AC voltage will be superimposed over the DC voltage values. So you think about, here is some DC value. We'll have some small AC value riding on top of that DC component. But in the small signal analysis, we just ignore the DC, right? It zeroes out. Okay. Now, you notice, guys, there's something I haven't talked about. What other elements did we learn about that obviously we have to deal with in a frequency domain analysis? Inductors and capacitors. I haven't even talked about those. How are we going to deal with conductors and capacitors in this class? Well, that's a good question. Let's consider that for a moment. So how are we going to treat those? Well, you guys remember in circuits 1, the impedance of a capacitor is 1 over SC if you've had circuits 2, or equal to 1 over j omega c. The impedance of an inductor is equal to S times L is equal to j omega L. So depending upon whether you've done Laplace transforms, you've used that S variable. But we saw this all before in circuits 1, certainly like this, where omega, of course, is the frequency of whatever sinusoid we were putting into the circuit when we're doing our analysis. So how are we going to treat inductors and capacitors? Well, first of all, I'm going to tell you that we're just going to ignore inductors. We're making it easy on ourselves. Why is that? Because inductors are rarely used in IC design. Unless you're building an RF circuit where you have to build a resonant tank circuit or something like that, you're not going to use inductors. Just about everything you're going to see involves resistances, capacitances, diodes, transistors. So we are just not even going to worry about these. We will ignore because they're rarely used. Now, of course, I'm cheating a little bit here. Obviously, we can't ignore them. All right? In high-frequency design, inductance matters very much. But for the purpose of what we're going to do in this class, the material we're going to cover, we're just not going to be addressing inductors at all. But certainly in more complex, in more advanced courses in circuit design, you absolutely would address inductors. We are, however, going to address capacitors. You're going to be dealing with capacitors. You're going to be building circuits with capacitors in your labs. So obviously you have to figure out how you're going to do those, what you're going to do with them. So in this case, we're going to make some assumptions. The magnitude of a capacitor is the magnitude of 1 over j omega c, which is just going to be equal to 1 over omega c. And here's the assumption I'm going to make. If omega times c is large enough, we're going to assume that that capacitor is very small. So I'm going to assume that either omega or c are going to be big, very big, such that that capacitance or the magnitude in that impedance is small. So let's, for example, consider how well does that assumption work? All right, well, let's think about that for a moment. Let's say I've got an amplifier circuit. And right now I'm not going to focus what's in that amplifier circuit. But let's just say here's an amplifier. And I have a resistor capacitor network. At both the input and the output of this amplifier. All right, now I'm going to make an assumption. Let's let f equal 10 kilohertz. Now 10 kilohertz is well within the human voice range, right? Human voice range is, from tens of hertz up to about 20 kilohertz. That's what we can hear. So this is right in the middle of things we would hear, music, voice, anything like that. It's not really very high frequency. Okay? So let's consider those two capacitors. For both those capacitors, the magnitude of the impedance is going to be equal to 1 over 2 pi times 10,000, omega is 2 pi f, times 10 times 10 to the minus 6. And if we calculate that, this is equal to 1.59 ohms. That is the magnitude of the impedance of those two capacitors. Now let me ask a question. If I am adding the impedance of 10K to 1.59, what is that sum of those impedances going to be with that resistor and that capacitor? It's about 10K, right? 1.59 ohms is going to have very little effect in series with a 10K resistor. Same thing out here. 1.59 will have very little effect in series with a 1K resistor. So what we're going to find is in this class, more often than not, in fact just about all the time, we're going to assume that the impedances of the capacitors are negligible compared to the resistances in the circuit. And therefore, we can treat the capacitors effectively as short circuits. So the capacitors will act like short circuits at all frequencies of interest, at any AC frequency we care about. So we're going to make it easy on ourselves. We're going to assume capacitors act like short circuits. Now, again, this isn't true, especially in advanced design. We will find that in more advanced circuit design, high-performance circuits, you can't treat the capacitors this way. You've got to actually consider their actual impedance. Now, if you do start throwing in capacitors and inductors and start considering how they behave in the frequency domain, well, then we start getting into something called frequency response, how the actual magnitudes change with frequency. And if you guys have had circuits too, you remember how we dealt with that. We did that by, for example, creating systems where we looked at poles and zeros. What's the frequency response of a circuit? How do filters work? We're not going to address that in this class. So if you haven't had circuits too, don't panic. It's not a prerequisite for this class. We're going to be sticking strictly with a situation where we're just going to assume we ignore the inductors and we assume capacitors are short circuits. Now we have a name for this. This is called the midband assumption. So we are assuming, in effect, that when you look at it, if you think about how actual circuits work, they'll have this kind of frequency response. When you look at frequency, you'll see typically this type of response, where they will behave very differently at very low frequencies, and circuits will behave very differently at very high frequencies. We're only going to worry about this region in the middle. And so we're just going to treat all of our capacitors like short circuits. So that makes things easy for us. All right? Questions? All right. I also, before we want to go any further, talk a little bit about biasing and our choice of biasing. Okay? As we've already seen, we have to have some type of DC source to bias up a circuit, to turn on the elements in the circuit. But it can it be any DC source? Can it be any value? Well, no, not really. Turns out the choice of our bias point becomes critical to how our circuit operates. Let's consider the problem of what we call finding the optimum bias point, or optimum biasing. In general, you want to set a cue point to give yourself the largest possible symmetrical AC voltage and current that you can in a circuit. We want to choose that point. So when we choose a cue point, we typically want to choose a cue point to provide the largest symmetrical linear region of AC operation. Now what do I mean by that? Well, let me draw a diagram to illustrate what that sentence means. Let us say, once again, I have some type of amplifier circuit. Right now, we don't care what that circuit is, but we have some type of circuit we're using as an amplifier. It could be an op amp, for example. And I'm going to be connecting that amplifier between a VDD voltage source, a power supply, and ground. And I'm going to have an AC input and AC output voltage. So I'm using this amplifier, for example, to amplify music. Small signal input with a small signal output. Now, this amplifier, what you're going to find is, if you were to actually do the large signal model of this amplifier, you'd find out that it's not a perfectly linear circuit. What do we know about amplifiers? Well, think back on op amps. Op amps saturate. Op amps cannot go past the power supply voltage or the ground in terms of the range of outputs. So if you were to actually go through and do a large signal graph of the response with DC voltages and DC outputs, you'd probably see something like this. So in this case, I'm going to plot Vin and Vout, and notice they're all uppercase. I'm going to plot DC values for Vin and Vout. And what we'd see is something like this, for example. You'd probably see something that looked like this. So you'd see something that close to the power supplies, you'd find that the circuit doesn't amplify very well. It saturates, the amplifier saturates. But when we get away from the power supplies, we'll have a range where the amplifier gives us lots of gain, lots of amplification, nice and linear. So when we think about it, let's consider consider this region here. Here's a linear region with high gain. So changing Vin causes a large shift in Vout. That's what we want from an amplifier. Okay. Now, you think about it. Where do I want to bias my amplifier? Where do I want to choose my cue point for my input and output voltages? Well, clearly I want to choose the cue point somewhere in that linear range. We do not want it to get close to saturation. We don't want to try to bias it down here or up there. It's not going to be a very good amplifier. But let me ask a question. Is every point in this linear range equally good? No, they're not all equally good. If I wanted to pick an optimum bias point, where would I pick it on that graph? Where would I want to pick it? Somewhere in the middle, absolutely. I want to pick an optimum cue point somewhere close to the middle of that range. Yeah?
Would that always be the inflection point?
Well, no. Well, different types of circuits will have different responses. I'm just saying this is a typical value, a typical example. But any type of circuit that's got a nonlinear response, you typically want to try to bias it if you can in an area where it's linear. So this is the optimal point. And why is this optimal? Because, if we think about this, it's optimal because if I pick this point here, and here's my Vn, then as I input an AC signal at this bias point, then what I'm going to get is I'm going to get a nice, large, symmetrical signal that stays on this linear region. So the optimum point is typically going to be somewhere near the middle. Now, you can't always get it right in the middle, but you always want to try to get it in a region where it's close. Now, you could, of course, go through and there we go. Also pick points here and here. Those are in the linear region, but they're poor because they're near the edge of the linear region. And so they'll very quickly, as you start to increase the amplitude, get pushed into the nonlinear region. And so what you'll see is if you're down here, you'll see you have a nice upper waveform, but one that's distorted on the bottom because we run out of room. And it goes in, the amplifier starts to saturate. Or I could pick up here. And in this case, I'll see that I have a nice, strong lower range, but then it starts to flatten out on the upper range and begins to distort because I run out of room. The amplifier saturates. So I can choose these, but these are poor. These are not good points. Typically, you want something in the middle. So the choice of bias is not random. Now, quite often in a problem, I'll just tell you what the bias is, or the problem will give you the bias point. But if you're actually going through and designing a circuit, you have to give a lot of thought about what is your optimum bias point. And it isn't just a consideration of the range, the AC swing of the signal. Sometimes it's also a consideration of things like power consumption. You know, what is your projected battery life? There are a lot of different things that can figure into what your bias point is going to be. All right? So you're going to see this over and over again. I bring this up now because it's an important thing to keep in mind. But I'm going to move on now, but we'll come back to this. You're going to be thinking about how to choose Q points later on as we start looking at transistor design. So we'll come back to this later, but I wanted you to start thinking about it now. Okay? Questions? All right. One other thing we want to consider. You know, when I went ahead and I did our problem a minute ago, I used the CVD model. What is our small signal constant voltage drop model of a diode? Well, we talked about the CVD model. The CVD model can be thought of as an ideal diode in series with a 0.7 volt offset, DC offset. And of course, if the ideal diode is on, then that ideal diode just becomes a wire, that ideal diode element. So this is what I actually have this thing behaving like in a DC circuit. It just acts like a 0.7 volt source. Except if I go to the small signal model, what does that turn into in the small signal model? A wire. Okay, so a CVD constant voltage drop model of a diode just becomes a wire. Boy, that makes our math easy. Everything is 0. Our math is easy, but it's not very useful. We do not use the CVD diode model in AC analysis for the small signal model. It doesn't give us a useful answer. It just turns into a wire. So what are we going to do? Well, this is actually the approach we just did a minute ago. First of all, we're going to use the CVD model to calculate only the DC bias point. So that should be the only time we use the CVD model, only to calculate the DC bias point. For the AC, the small signal calculations, we're going to use the exact dynamic resistance equation we've already calculated. So I use a reasonable approximation for the DC calculations because it's easy to use, and it's only a few % off. But for my AC calculations, there's no reason why I can't use the exact dynamic resistance model. It's a simple equation. This is what we did in our previous example. This is what I expect you guys to do when you're doing, for example, homework problems or problems on the exam. Make it easy on the DC analysis. Just use constant voltage drop. Make your calculations easy, but then switch over to the exact small signal model for AC calculations because it's still mathematically easy to use. All right, so just want to separate that. There will be many times when we're actually going to use a significantly different model or a different shortcut for a DC calculation versus an AC calculation. There's nothing wrong with that as long as we're reasonably accurate. In this case, we're saving ourselves a great deal of time and effort in terms of the calculations. Now, I want to point something out. In the example we just did, we did a DC bias point calculation. Then from the DC bias point, we plugged our IDQ value into our small signal model. And then we did our calculations. So first we did DC, and then we did AC calculations. I point this out because guess what also uses this exact same type of calculation? An AC analysis in LTspice. This is exactly what LTspice does. So for example, in the pre-lab you guys did this week, you specify a DC bias value plus an AC value on the source when you did the AC calculation. That DC value set our bias point. Then once the bias point was calculated, then it did the AC calculations. And of course, in this case, LTspice in the AC domain does calculations versus frequency. And so you will see, for example, voltages and currents will change with frequency. And that's the influence of the capacitors that are actually in the model that you're simulating. All right? So you're already seeing this type of thing. This is exact. And if you do not put in a DC bias value, your AC analysis won't work because you're not turning your circuit on. You've got to turn the circuit on. You've got to bias it in order to get a meaningful AC result. All right? So just want to point this out exactly what it is an AC analysis is. And of course, when you're doing this with respect to frequency, you'll see poles and zeros. So this is all the circuits 2 stuff. That those of you who've had circuits 2, you've seen that before as well. But in general, we're not going to be worrying about frequency response in the types of circuits we're going to look at. We're going to be looking at circuits where the frequencies are low, and typically the response of the circuit changes very little. All right? Questions about this? Yeah?
When would n not equal 1?
Well, n cannot equal 1 depending upon the geometry and the type of diode. We're always going to assume n is equal to 1, but when you look at actual diodes, n values anywhere from 1 to 2 can exist depending upon the type of diode, and that's typically going to be built into the model. So one of the things, for example, the 1N4148 model, if you look at it, I don't think n is exactly equal to 1 in the 1N4148 model. I think it's like 1.1 or 1.2, but it's not unity. But you know, we are assuming unity here, but that's what I'm saying. The hand calculations versus what LTspice will tell you, depending upon the model, can be different than what you expect, because not all of those values are going to be the assumptions we are making in this class. In fact, I think in one of the problems, you're going to be asked, or at least at some point in one of the labs at some point in the future, you're going to be asked to actually calculate n, the value of n, depending upon, in fact, I think it was in this lab, when you did the DC plots of the diode, you're going to calculate n according to what you measured off of the AC versus DC plot on the Elvis units. So you can actually calculate that and see, is it really equal to 1? Well, you'll find it's not really equal to 1. Okay? Any other questions? Yes? Oh, the Y is going to be either voltage or current. Okay? In other words, the magnitude of some voltage or current in the AC domain. It's going to vary with frequency. Well, yeah, well, in any capacitance or an inductance, anything that is going to, the impedance changes with frequency is going to affect that response. But once again, that's beyond the scope of this course. Take circuits 2, or pardon me, electronics 2 from Dr. Massengill, and then you will learn a lot more about the actual frequency response of amplifier circuits. But we're just going to cover what we call the midband assumption. We're going to make things easy on ourselves. Okay? Anything else? Any other questions? All right, now, I'm going to leave behind small signal analysis for the time being. There's a couple of homework problems with small signal analysis. You're also going to have a small signal analysis thing with diodes in next week's lab. So we're not leaving this stuff behind, but we're going to move on to other topics for now. We're going to come back to this in a big way whenever we start looking at amplifier circuits and start looking at transistors. So we're going to step away for now, look at other topics, but we will definitely come back to small signal analysis. Let's look at some other applications of the diode. And one of the things I want to spend some time talking about is voltage regulation. Now, voltage regulation is a big topic of a lot of importance in circuit design. The idea is pretty straightforward. You're going to have some voltage regulator circuit. And the input of this voltage regulator circuit can be some DC voltage that tends to vary. In other words, I'm going to say that this is an unregulated DC voltage. And there are lots of examples about this. For example, you have a solar cell. You take that solar cell and you put it in the sun and you measure the voltage across that solar cell with the sun shining on it. Get a nice steady voltage. You take the solar cell and you bring it inside. And now you measure the voltage under these lights here, and you're not going to see the same voltage. The voltage of the solar cell is going to vary depending upon the operating conditions. So you may have an unregulated DC voltage, but the point is you have a circuit that needs to have a constant voltage. And so we have circuits called voltage regulators that, given an unregulated input voltage, give you a constant or regulated output voltage. So voltage regulators are clearly something that circuit designers care about and system designers care about, because you want to have a particular voltage that you know is going to be constant. But you're not always going to be running off of a voltage that is constant. So you have to regulate it. Well, it turns out diode circuits are great for regulation. Let's look at some simple concepts. Let's look at this. So let's say I've got a simple diode circuit connected to a resistor to a 10-volt source, and that is our input power supply. Let's let N equal 1. Let's let IS be equal to 1 femtoampere. And I want to calculate the voltage at this node VO, which of course is also equal to the voltage across the diode. Now, if I were to do iterative or exact analysis, what I would get is the following. V0 would be equal to 0.689 volts. So again, I'm not using the constant voltage drop assumption. I'm actually iterating it and assuming I actually got the correct value. So I did not bother to go through the iteration. You guys can do that. But that would be the answer you would get. Okay, now, what if I changed that voltage value? Let's change that 10 volts to 5 volts. So I'm going to lower that voltage to 5 volts. Now what is VO? Now VO becomes 0.670 volts. And once again, that's an exact value. So I took my input voltage and I cut it in half. I reduced it by 50%. And yet the output voltage went from 0.689 to 0.670. In other words, delta VO per delta VDD is going to be equal to, in this case, only 0.689 minus 0.670 divided by 5, which is clearly going to be a nice small number. And in fact, let's now take this and now let's let VDD go to 10 volts. And again, recalculate V0. Now the exact value is 0.700 volts. And now, therefore, delta V0 over delta VDD is equal to, in this case, I want to go from this value to this value. So I'm going from 5 volts to, 15 volts. My apologies. That should be 15, not 10. So I'm going from 5 to 15, and I'm going from 0.670 volts to 0.700. So I'm going over a wide range. Let's do that calculation. That's going to be equal to, in this case, 0.7 minus 0.67 divided by 10, a 10-volt sweep. And this is equal to 0.003, which is equal to 0.3%. And there's my result. So in this case, I just went ahead and just did the calculation all the way from this point to that point to get the widest range of variation, from 15 to 5 volts, with 10 volts the median value. So we notice how it changes. It changes very little, and over that very broad range, I get only a 0.3% change. Well, this is good. What we have here is a circuit where I have an enormous change, plus or minus 5 volts, plus or minus 50% value shift, and yet the output only changes by 0.3%. That's a very desirable result if you need to have a stable output voltage. Now let's calculate this in a different way. Let's go back to this original circuit. And I'm going to calculate this not by using these exact DC values, but by treating this as a small signal AC circuit. What I'm going to do is this. I'm going to take this 10-volt circuit and add a delta VDD to that circuit. And what I want to do is I want to calculate this in the small signal domain. Okay, what is delta V out given the delta VDD? Let's do a small signal calculation. All right, so for my small signal calculation, I'm going to use the CVD model first. I'm going to assume for a CVD calculation that IDQ will be equal to 930 microamps. So in other words, that'll be equal to 10 minus 0.7 divided by 10K. I'm just assuming the voltage drop across the diode is 0.7 volts. And then I go and, given this, I can now draw the small signal model. RD, I can calculate. RD is going to be equal to VT over IDQ is equal to 26.9 ohms. And now I'm going to calculate delta V out over delta VDD. And what we get is that delta V out over delta VDD will be equal to voltage division, 26.9 over 10,000 plus 26.9, which is equal to 0.00268, which is equal to 0.268%. So I just did this calculation not using the exact DC values, but using an AC small signal model. Notice this answer versus that answer. Which of those is the more accurate answer? the one on the top. I did that using the exact values. Why doesn't this one match? Because it's assuming the diode is linear. And so therefore, it's not as accurate. But here, let me ask you guys a question. Is it close enough? Would you consider 0.27% and 0.3% to be close enough where you could use that AC model? Sure, yeah. So here is an example of an alternate way to calculate the regulation of the circuit using AC instead of DC analysis. Not as accurate, but sometimes can be a lot faster and simpler. Okay, so next time we'll come back to this and we will look at more regulator circuits. Given this idea, how can we make this circuit even more useful? And then we're going to look at the Zener diode. We're going to return to the breakdown region of how diodes work. See you on Thursday.